Okay, let's just do a couple of illustrative examples. Let's say that your mass, you as in person, your rest mass is 75 kilograms. That seems reasonable. What is your mass in MeV per c squared? So therefore, your mass, M0, is 75 kilograms times 1 MeV per c squared over, sorry, our unit conversion is for EVs per c squared, 1 EV per c squared over 0.178 times 10 to the minus 35 kilograms. That's a 35. So that equals 421 times 10 to the 35th EV per c squared. So writing that as MeV per c squared mega electron volts, right? So that's going to be, and then let me just first do 4.21 times 10 to the 37th EV per c squared, which is 4.21 times 10 to the 31st mega electron volts per c squared. Okay. So then what is your rest energy? In other words, right, or another way to look at that is how much energy could we get if we annihilate you? And then we did this for Nick in another class, right? What is your rest energy? Well, no calculation here. The rest energy, E0, is 4.21 times 10 to the 31 MeV. You might want to know what is your rest energy in joules. Okay, so then we do the conversion. So, and I didn't ask for the units, but I'm just going to do it in both unit systems. 4.21 times 10 to the 31 m mega, 1.6 times 10 to the minus 19th. An electron, coulomb, times a volt, V. And so that gives me 6.73 times 10 to the 31 times 10 to the 6th times 10 to the minus 19th joules. So I just multiplied the factors of 10 separately. And so that's 31 plus 6 is 37, minus 19 is 37, 27, 17, 18. So it's 6.73 times 10 to the 18th joules, which should be somewhere around what we had found as the rest energy for Nick in the other class. Okay, let's say that we've got an electron in a particle accelerator. And the electron, we know the electron mass, and it's traveling at 0.1 c. But let's say I want to increase its speed, and I double its total energy. How fast is the electron going if I total the double energy? If I double the total energy. Well, total energy is gamma m0 c squared, right? So if initially, we can say E initial is gamma initial m0 c squared, where gamma initial is the square root of 1 over 1 minus u initial squared over c squared, right? The initial speed. This is the initial speed. And so gamma final is gamma f m0 c squared. Gamma final is square root of 1 over 1 minus u final squared over c squared, right? So, if the energy doubles, then EF over EI is equal to 2. So therefore, gamma F over gamma I is equal to 2. Right? If we just do that math. And so we can figure out that therefore, gamma F must be 2 times gamma I, and we can go ahead and start plugging in 1 over the square root of 1 minus u final squared over c squared is equal to 2 times 1 over the square root of 1 minus u initial squared over c squared. And so we can square both sides, invert both sides. So 1 minus uf squared over c squared is equal to 1 minus ui squared over c squared over 4. So this should be a therefore, this should be a therefore. And ui was 0.1. Remember, ui was 0.1 c. So therefore, 1 minus uf squared over c squared is equal to 1 minus 0.1 squared over 4. The c squareds cancel. And so therefore, we can do this. This is 0.99 over 4. If you do that out, and so therefore uf squared over c squared is equal to 1 minus 0.99 over 4, which is equal to, pause. So we get that, and so therefore u final is equal to 0.7525 c squared, square rooted, which is 0.87c. 0.87c. Pretty sure I got that right. So notice that in order to double the total energy, if we double the total energy, the final velocity is a heck of a lot bigger than the initial velocity. But that has to do with the fact that the part of the energy is mass energy. So we could have said, what if we double the kinetic energy, and we would have gotten a different kind of an answer. But anyway, that's just an example. So the last energy example I want to do is just something related to nuclear fission or nuclear fusion, and seeing why do we get out energy in these reactions. Fission is the more common kind of reactor that we use in order to create electricity, right? We call it nuclear energy, but it's electricity. Fusion, they're still trying to develop fusion reactors, but we have both fission and fusion bombs, right? Where we get out a lot of energy from the splitting of or the combining of subatomic particles, right? Fission is where we split an atom, right? We split an atom, so it goes into two or more smaller pieces, right? That's fission. We basically, split an atom. Fusion is where we fuse two nuclei together in order to make a larger atom, right? So what we get out is a larger atom. I guess what we get out is splitting. Okay, so this is fusion, where we put together two nuclei and to get out a larger nucleus, and this is fission, where we take a larger nucleus and we split it into two or more smaller nuclei. Okay, fission is an easier reaction for us to control. Fusion is a harder reaction for us to control, which is why we have fission reactors but not fusion reactors. But we can do fission and fusion bombs because we don't need to control those reactions because we want it to be an explosion. Okay, hopefully that makes a little bit of sense. But the nuclear reaction can be written as... So the typical fission reaction in a nuclear power plant might be something like uranium-235, which is naturally occurring, and you combine that with a neutron in order to make it uranium-236, which is unstable. And so the uranium-236 will then fission. It will split on its own into kryptonium-93 and barium-141 with some additional energy. And it's the energy, that's the energy that gives you the nuclear energy that is creating electricity, or nuclear energy that's creating the atomic bomb. So let's just figure out how much energy this reaction will give us. So what I'll start with is uranium-236, and the mass. This is a stationary isotope. I mean, stationary in the sense this isn't an accelerator or anything. This is... Sorry, I just pushed pause. I don't know when. This is the uranium-236 is stationary in the reactor, stationary in the bomb. So it's got a resting mass of, and I can look it up. And I'm not sure how many decimal places we need for this, but I'll carry it out to 4. 236.0456 AMUs, atomic mass units. And then I'm going to look up krypton. Did I say kryptonium? Krypton and barium. Whoops, I wrote that down. That's krypton 92. Krypton 92, not krypton 93. Okay, so I think I got all the information here. The masses in atomic mass units and the conversion from atomic mass units to MeV per C squared. I just looked that one up. I'm just going to keep, so remember, we're not worrying about the neutron plus uranium-235. I'm just going to compare the uranium-236 to the reaction where we get out the energy. And the mass here is 236.0456, and the mass here is the mass of those two added up, so we have to add up the 140 plus the 91. So you can see that mass is not conserved because mass is turned into energy. Right? So there's a certain amount of mass that's missing, and that mass is energy. Now this is still in AMUs, but the amount of mass that's missing is the 236 minus the 232. And we could do the fractions, but it's about 4 AMUs, right? 4 AMUs of mass is missing. So that is how many MEVs. If the AMU, so this is the mass, so the amount of mass that's missing in MeV per C squared is 4 AMU times 931. I'm just going to keep to the 3 significant digits. 931 MeV per C squared over AMU. So we've got 4 times 931. It's 3.72 times 10 to the third MeV per C squared. So the amount of mass missing is that, and that mass is turned into energy. So how much energy is created? The amount of energy created, this is where we can just say, oh, well, so it's 3,720 MeVs. So therefore, it's, right, so it's the total energy that's released in this reaction is the amount of mass that's missing times C squared, MC squared. It's not moving, so the mass wasn't moving to begin with, so it's just gamma equals 1. So it's 3,720 MeVs. That's the amount of mass, that's the amount of energy that is released for each U-236 that naturally decays to the krypton barium plus energy. And so now, right, so that's where we're getting energy from. It's mass turned into energy. And that's where the energy comes from in these nuclear fission reactions. In fusion, it's the same thing. In fusion, there are some things that prefer to be apart, and there are some things that prefer to be together. In fusion, you take two elements that would prefer to be together. They're a lower energy together, meaning that they must emit energy when they fuse instead of when they fall apart. But this is the nuclear reaction, and that's the amount of energy per atom. Now you might ask, what about joules? Well, you can do the conversion, right? It's not a lot of joules, right? But this is a single atom. Now you get, I don't know, a mole of the atoms together, and now you've got a fair amount of energy that comes out of a nuclear reaction.